AI team at Nearmap. And on that note, I also want to, which is probably doesn't come as a surprise, but we are also hiring for multiple positions for ML engineers, both in senior and mid-senior capacity. If you are interested, please reach out to any of us, or even if you go onto LinkedIn and find Nearmap, a bunch of job opportunities will be there, and we can have further conversations. And without further ado, let's start the next session of this today's evening, and this is the panel discussion. And I realized I haven't introduced myself, so I should do that now after half an hour into meeting you. I am Sunita Kamal. I work as a director of AI model systems, and my team essentially is responsible for work on data systems and also looking at how that feeds into the training and the training applications and deep learning side of things. So more a systems view of what we do at AI, but we sit more on the deep learning and everything that goes under the hood from that point onwards. Yep, so like I said, our team is here, and please feel free to reach out. Yeah. So I probably want to do a bit of a preamble leading up to the discussions, and the preamble starts now. So the data needs are ever growing, and today what we are doing is we are producing more data than ever, and we want to combine them all together to do something that has never been possible before. And while a lot of exciting development is really happening all around in every single field, one particular field has stolen all the thunder, and we are basically talking about this maths, ML, and AI. And it's a bit of a shame because that's not where all the exciting development is happening. So I kind of want to bring your focus to what's been happening in last 12 months or so, where there are at least emerging streams that's coming up, and they are appreciating the value of thinking about data, thinking about curation of the data, and acknowledging the value of it. So yes, that has been said that data is the new oil, and that is definitely a principle that we believe in as a Nearmapper. And if you haven't heard about concepts around data-centric AI, data engineers, Andre Karapati from Tesla talks about, that is all speaking to and recognizing the underappreciated value of data. And on that note, I would probably say this panel is very much focused around appreciating and acknowledging the power of data and what we can do if we really value the data in its own capacity. So today's topic really is what do we need to do to make a successful data systems? And we have a bunch of panelists who come from a very diverse background that works on a different lenses of data, and we will go through a series of questions and hear their perspective on what do they think from their experience that makes a good data system. So on that note, let me introduce you to the panel. We have Nagita Meher. She is the director of AI model R&D. Nagita, do you want to join us on the panel? She has many years of experience working on commercial and research, deep learning techniques, and computer vision. She has PhD in scalable video compression, and she has pretty much worked on every single aspect of computer vision, deep related technique. And with that experience, she leads the R&D team at Nearmap. And next we have, probably this name is not new to us, to any of us. He is one of the team, sorry, of the data engineering meetup, Simon Aubry. Simon works as a principal data engineer at ThoughtWorks. He describes himself as data geek, and he also describes that to his kids, who probably don't appreciate the value as much as we do. But he is very excited to be in data space, building distributed data systems, solving data problems in many different domains. And recently, he has been more passionate about working at streaming technologies and also building human-centric machine learning systems. And as it doesn't surprise you, also talking about data mesh architecture that's really stemmed from ThoughtWorks. And then we have aureus. He works as a principal machine learning engineer at Nearmap. He works in my team. He also comes from a diverse background in software engineering and data engineering space. He has been focused on building data analytics solutions, and machine learning solutions in the domain of manufacturing, finance, and many more that I probably would not count. And he works, like I said, he is working towards building the data platform that powers deep learning systems at Nearmap. And last but not the least, our very own Peter Hansen. If you can finish the setup, Peter, and join us here, that would be really good.
Awesome. Cool.
I think this guy needs no introduction. Pretty much everybody in Sydney knows him well, but I will do my job and introduce him. He is the community leader of and founder of data engineering meetups in Australia. He is also serverless hero, and every now and then we keep hearing about the good things that he has been doing with AWS technologies. And he has founded two consultancies, Cloud Shuttle and Cloudseer. If you are in struggling particularly with data problem, you know who to find. And with that, I think we quickly, any questions so far? No, so we go into debate point one. And this is the point when we start talking about what are the characteristics of a good data systems. And I would like to start off with Nagita. And the reason I should explain the reason why I want to start off with Nagita is because she sits on the side of data systems where essentially she's applying the consumer lens. She is the user of the data, and uh, a successful data system should be built in a way that she is happy. So I think I want to spin around and listen to Nagita to what is her definition of a good data system. So Nagita, if you can please speak to that.
Thanks, Anita. It sometimes feels weird to hear me referring to as a customer when we're all working in the same team.
Please speak up. Thank you. Yeah.
Let's get that one. Sorry. Tom was saying data is the fuel. You're saying data is the new oil. I'm going to use a different term, saying data is the lifeblood of AI. Is that not working? Is it working now? Okay. And
Very close, unfortunately. Like you've gone to karaoke.
that was not interesting. And one of the key things that attracted me to Nearmap specifically was like the sheer amount of imagery data that Nearmap owns. If we consider a life cycle of building a new AI solution, often the process, after you map the business requirements to an AI solution that you can tackle, often the process starts with we want to find some examples of the things we want to do, get them labeled by human expert labelers, and then train a model on that. Often what you need next to make the accuracy above what you were doing on the first stage is being able to find all the weird corner cases and edge cases and weird things in the real world. This is what I'm going to refer to as a feedback loop. And to be able to satisfy various different AI needs, we often need multiple of these feedback loops in AI systems and in a data engine. I'm just going to give you an example. Like Mike was talking about training a model on a data set of close to 1 million human labeled images. So we had the model, it was doing 40, 50 different classes, roof, solar panels, roads, vegetations, various different classes. The accuracy on solar panels and swimming pools was about 99%. So pretty much done. Like that's what you usually say that's good enough for any system. And once we had the model deployed in the product in a prod, using this feedback loop, what we realized is that, for example, there is a type of pool cover in US, which is just gray with a rectangular pattern on that. I'm guessing they do it so that they can cut it accurately. But that gray sheet with white rectangles on them looked very much like a set of solar panels. So the way to find these kind of weird cases is really by having that strong feedback loop, which then mines the data for you in the prod system and be able to find all these weird cases. Just another example, like if you want to, say, build a model to detect construction crane, if I randomly pick a point across US or Australia, what's the chance of having a construction crane close to that? Pretty close to zero. So if you just want to samples and look for an examples to send to human expert labelers to label, that's going to take a very long time and it's going to be very efficient. That's where you need to build on the feedback loop in the actual prod system and be able to find the things that you want more efficiently. As a user of the data engine, what I would like to be able to do is just interact with this complex data engine with multiple feedback loop by setting like a simple config file, for example, as an example, and then get the data that I want mined from, say, 1 million square kilometers of imagery, which has been processed, say, by a previous model, find what I want, maybe run another simple config to sample from that and do like the final selection, send that to human labelers to label, and then build the next training data sets for the next generation of the model. So being able to just mine and label and get the data we want for training is like a key thing we want.
Thank you for that, Nagita. And I think if I can summarize, essentially what you're saying is you would like a system that masks all the complexity of doing the data crunching at scale and providing a very easy interface where you would want to be much more clever and methodical to what data you want to give labels to label on rather than, say, randomly sampling. And you are not talking about just algorithmic approach to sample. You are kind of saying, let's bring the model in and that model tell us where we are doing poorly. So that's a very interesting space, and it's something that we are also trying to, like at Nearmap, we are trying to do a lot better on. But as you can see, the challenge is really it's a meaty challenge. It's really hard to hit that, and I'm sure other organizations are practicing that in a different capacity as well. So what I want to do is I want to go around to these three folks who are very much special in the data engineering, data space, and software engineering space, and I want to hear from them what should we do to build that system that meets Nagita's need, and also if they have any interesting perspective around that. So Saman, let's go in the circle. Why don't you start?
I'm in front of a microphone. This can only be dangerous. I loved hearing from Nagita. This was a really, really good idea and really thoughtful answer around what does it mean for a solution when we're talking about a product or a consumer. But I wanted to take the question in a slightly different direction. I kind of wanted to talk about what good looks like in the real world. We should actually be talking about how things get to production in the first place. I read a quick quote. 87% of data science projects never make it to production. 87% of data science effort never makes it to production. So when we're talking about good, let's think about firstly, what are the challenges that prevent that code, that effort from going through to production to actually make someone like Nagita's life easier and happier. So let's think about the problems that stand between the data science world and production. We're talking about things that I get to see in everyday life, things that get in the way. Manual, fragile processes that are very slow. The gaps between the notebook and production. Data scientists in siloed teams working independently from engineering and deployment and platform teams. There could be lack of infrastructure, things that stand in the way of scale. Lack of observability, feedback loops, and confidence in the outcomes. And once things are deployed, that can't be the end of the road. That's the beginning of the road. We're talking about re-evaluation, model experimentation, survivorship, feedback loops. Those are all the things that get in the way. One, some, or many of those things can prevent something getting into production. So what's the answer? Now, there's a whole bunch of language. I like to use language around CD for ML, continuous delivery for machine learning. This is no different to continuous delivery that we see in software engineering. Deploying ML models becomes a business decision, not a technical barrier. So how do we adopt those principles and those practices of CD and deploy them and have them help us on our way when we're talking about that fast loop and feedback loop for machine learning to value? So I don't want to bring problems, I want to bring solutions. So when we're talking about what does a good data system look like, it means automating everything from day one. Building quality in, building observability in, building testing in from day one, and having that repeatable, auditable process. And when I work in data teams who are doing this, we actually talk about deploying a null model to production on day one. We want to be able to build everything from beginning to end, have observability, feedback loop, confidence that you can actually go from development through to production before we actually touch any machine learning code. And having that as a boilerplate and as a framework really helps us bring value very, very quickly. It makes Nikita's life a little bit easier.
It's an interesting viewpoint. I think what's more aligning to is the whole end-to-end like CD pipeline, as you said. But I think if we spin around a little bit to Nikita's question, the part that I'm hearing is how can I find this thing and do that crunch at scale, which is, I think, I agree with that. That's the big picture, and that's what definitely should be at day one. But if we kind of try to zoom in into that particular space and say how to build a system that can scale to do a data crunching, but that query itself is a little loosely defined. What's your view around that? Just Simon, on to you.
Oh, how do you build things at scale? And
yeah, so like a interface, a query interface where you kind of like, how Anagita alluded to, you have a config where you specify your, this is the kind of data I want. Say swimming pool that overlaps with solar panel, and I want to run it with a really large data set.
Oh, absolutely. Again, using a lot of the learnings that we've had from continuous delivery, we start with a test case. What is the outcome? What is the expectation? What's the definition of success for this model? Build the definition of success first and get the model to fit the test case. Again, I sound like a broken record. This is CD for machine learning. So very much that mindset of test-driven development and the confidence that you can keep evaluating and having that feedback loop.
Yeah, cool. Thank you. Thanks, Simon. Hi, you are next in.
Sure. Let's see if I can take a stab at trying to solve the problem. I think what Simon was talking about, using CD for ML, is a very interesting concept. And it's interesting because a lot of software engineering concepts and the way software engineering practices have evolved over the last few decades can be borrowed over and used in ML to alleviate a lot of this pain. For example, a lot of problems at the end, if you really closely listen to what Nandita was talking about, has to do with how we define the tooling interfaces. How do we make them simple? How do we have the right level of abstraction while still giving them flexibility and control over what they want to do? So, for example, these kind of systems, when we start out, may seem very simple. If you're building a deep learning model, you might want to start with a simple system that builds a data set and then go from there. However, I think the real key here is from day one, try and build the system that can tackle the issues that we'll see 3 months, 6 months, or 3 years from now. A lot of people have talked about the incredible journey that Nearmap has had, especially in the field of AI. I think it's important to note that 4.5, 5 years ago is when data science project or a data science research project is how AI at Nearmap started. And within this small window of time, it has gone from a research project to a full-blown production deployment of a deep learning model that is serving petabytes of data to real-world customers who are paying for it. And we are now in the mode where we are constantly trying to deploy newer generations of models, try and solve at every generation, try and solve a more nuanced problem, derive more nuanced knowledge. So the system that you built 3 years ago would not be purpose-built for what we're trying to do now. The crane example that Candida talked about was quite interesting because think about the mindset of data scientists 3 years ago when they were just starting out to see, can we solve semantic segmentation for swimming pools? And all you had to do was look at, oh, can I get census data, find where the swimming pools are, which are suburbs, get suburban data, and train your model. 3 years on, that doesn't cut it anymore. We have to now think about how these systems give you exactly the same kind of interface, but do much more. They try and solve the problem of find me the 10 cranes in a 100,000 square kilometer area. And that's the key. You have to build the systems on day one so that they can evolve over time.
So essentially what you're alluding to is when we start building data systems, we have to keep the view side of what is the future like and build for future. Yeah. Fair enough. Your turn.
It's my turn. Yeah. So I think, some of the chaps to my right have been alluding to the fact that sort of data engineering, machine learning are increasingly borrowing a lot of these software engineering concepts and methodologies like continuous delivery for machine learning. And so we're seeing a lot more and more embracing of software engineering practices. And I think perhaps one of the more rudimentary practices that a software engineering team would implement when developing, say, a web app or something like that is implementing things like Zendesk, for instance, where you're getting sort of direct end user feedback and sort of collating all of that. You've got a project manager that will be going through all of that feedback and going, okay, I've got this team of engineers, they're usually quite well paid. I can't just get them receiving all of this feedback all day long and just sort of changing what they're working on from day to day. We need to sort of, look at the backlog, understand what's the priority, what's the order, of prioritization to fix these kind of issues with the machine learning. So just having those, feedback loops in your data systems, and then I think more broadly just having that observability occurring. So I think in this particular instance, I think the machine learning model was trying to detect solar panels, and then it was mistakenly that machine learning model was developed, wasn't it, in Australia, when it was brought across to the US, because they've got particular pool covers that look very similar to solar panels. That caused like the machine learning model to sort of, incorrectly label, the pool cover as a solar panel. And I guess, there's potentially ways of measuring, comparing from an observability perspective, say the measurement of the solar panel and stuff like that it's incorrectly labeled, these sorts of things. So there's a whole bunch of ways that, potentially we could look at feedback loops to help improve these processes. But I think more specifically, potentially just having that way to collect when you've got sort of human in the loop labelers, have that sort of Zendesk type capability, if you will. I don't know.
Yeah, it's a good point. It's something that has come up for us as well, where we talk about the tool that our end users use to visualize the predictions. So they can say, like, this space is wrong, and they can give a direct feedback. So sort of like Zendesk, but more inbuilt. You can give the feedback in time. Cool. So thank you for taking up Nagita's point as a challenge and thinking about how we can do this. I haven't forgotten that we talked about characteristics of good data systems. So let's go around to three of you and hear if you would like to add anything to what are the characteristics of good data system. If you don't have to add anything, that's all good. But if you have, then...
Yeah, so characteristics for me of a good data system is having solid data platform foundations. When you're onboarding data into your data lake and sort of, further processing it down the line is to just make sure that you've got really good labeling and categorization first up. There's PII data and stuff like that. In the AWS ecosystem, we see, unfortunately, from time to time, inadvertent data leaks, and I think a lot of that could be avoided by having a very well-structured data lake infrastructure that's categorized. Okay, this customer data that we're onboarding, we're going to put that into the S3 bucket that's, confidential or something like that, confidentially labeled data sets. And so I think, when you're really sort of having that data platform thinking, and I think that's maybe we need to change the name of this meetup to data platform engineering instead of data engineering, because I think that's really where data engineering is pushing towards. It's not so much that data engineering is, just sort of doing data pipelines, because a lot of data pipelines with Fivetran and the like, that's all automated. What's really actually critical in a lot of companies that I particularly work with is just setting up that foundation where folks can sort of onboard data quite easily in a way that your future self will thank you for.
That is actually 100% right, and I would vote for it. And that is also the platform that Ari is building, and we are hiring, just being very overly picky. But over to you, Ari.
Yeah, I think it's kind of interesting if you ask a diverse group of people, what should the platform look like? The answer would inevitably be very different. And it has to be different because the use cases that different companies, different organizations, and different teams are solving are going to be different. And I think the right question to ask is, how do we get to the data platforms that Peter was talking about? And I think there's like two cornerstone principles that we should derive our inspiration for a platform design from, and that is talking to the customer, talking to Nagita in my case, and understand the domain. And even though the first one is super easy, the second one is usually quite hard. A lot of times we as data engineers or software engineers tend to think of problems in isolation and have that idea of, I will sit down and obviously, surely, how hard can it be? I'll just drum up a solution. That's not how anything works. I think the important bit to understand is, especially in data engineering, and especially when you're trying to solve deep learning problems, you need to understand the domain so that your architecture and the design of the application is purpose built, so that when you actually get to your customer, when you're talking to data scientists and you get a request from them, you are able to build up the right abstraction and interfaces which allow them to move super fast. Because just building domain-driven applications is not enough. I think one thing that's specialized when it comes to data engineering and data engineering for deep learning is something which is different from standard software engineering. Is we have the huge amount of innovation pressure. With every iteration of the model, with every month that passes by, there's huge amounts of innovation that is going on in the industry, and the innovation makes its way into how we do the next iteration. And for that, understanding both the domain and your customers is imperative. So I think that's how you get to a system. I can give an example. One of our training dataset systems is kind of built with the idea that we know what are the use cases today, but you're building in the data searchability into it for the use cases of 6 months and a year from now.
That's a very good point, and also very challenging point.
We have questions there, Sunita.
Yep, sure.
I'll pass on the mic if you don't mind. Cool.
Also, while you're going to pass the mic, we have lots of giveaways, and they were essentially for the questions. So one coming up right to you.
Thank you, panel. My name is Faison. I know we're talking about the characteristics of building a successful data system, but I just want to take one step back and direct the question to Nagita. at the very first kind of question of her mentioning a data or a feedback loop, can we get a specific example of how a data or a feedback loop has helped to deliver in real life, meet the demands of a growing independent deep learning system? I know that the other panelists talked about a swimming pool with a black rug and running some AI on that to detect black and whatever the things you got to do, but one real life specific example of how it's met the growing demands of a deep learning idea. Thank you.
You want to use that mic?
The mic's coming back again.
Yeah, that was the longest work. Thank you so much for that very good question. I think that it also gives me the opportunity to go back to what Simon was saying before. So in our system, basically on the inference side of things, where we actually have a model deployed and you're running it across every server that you're capturing, as part of that running, we also have another system which basically looks for things which, based on some config that I'm calling it, finds the cases that the model is not doing great. Okay, and to find that is you could be looking at various different things. You could be looking at the entropy of your prediction. You could be looking at low prediction, like low confidence predictions. You can bring in ontology and then look at the things which should or shouldn't occur, even like probabilistically, and then sample for all of the cases where I think some or one or multiple of these rules are breaking. By doing that, that system is just collecting these samples for you, and those goes another like a S3 bucket. That is done. Once that system is built, that is being done. It's just working without any human effort into it. As we process every survey, we're also collecting samples in some S3 buckets. And those samples are the samples which break some of the rules that we have specified. These are the things which we want to look. Once the samples are collected, then that's a data science exploratory task. You go to those samples, look for patterns in those, see what is the common occurring pattern in those samples, and basically form like a unit test. So we're talking about using the software engineering concepts in the data science as part, and it's like a data unit test. You form a unit test saying that corner case was a challenge for my model. Now I need to develop my model so that it passes that unit test, so it's not making that same mistakes. And that's how you actually sample from those things which are just being automatically mined, label that, and use that to train the next generation of the model. Am I answering your question?
Still very generic, but I feel,
Maybe I can add to that. So I think if your question more is, maybe I can add to that. So if your question
just
more,
one real life example.
Yeah, sure.
Just
Yeah.
instances.
Yeah, sure. So say your task is that you are detecting poles and you really want to give your end users, your customers, where the poles are. So you build a model for poles and you run it, and your algorithm would tell, and you basically give lat longs to your customer. But say pole look like could give you a false positive for fire hydrant, and if you didn't, initially you didn't know, you trained your model, you put it out in the wild, you realize that actually my model hasn't seen enough of the fire hydrant to know that that's actually a false positive, not a true positive. You really need to pull that back in to teach your model that now I only want you to detect power poles or light poles, not fire hydrant. Still sticks up the ground, but not fire hydrant. You need to pull that sample back in, train your model again. So next time when you give your data set to your customer, now the customer is not worrying about the noise because your model is performing much better. And that's the value of the feedback loop and the data engine. So it speaks to building better model to solve the customer problem more efficiently. And why you may or may not need it depending on how, how constrained your problem space is. For the space that we work in, our problem space is unconstrained. We are capturing basically our real world and we are predicting on the real world, which is different to images of cats and dogs, which is much easier. So not to say that any problem is less or more important, but depending on the enormity of the challenge you are dealing with, you might be having to handle that sort of complexity and deal with the feedback loop aspect of it.
Thank you.
Sorry, I wasn't meant to be on the panel, but I couldn't avoid answering. Anybody else wants to add anything? No. How are we doing for time, Peter?
Yeah, I think we're fine.
Yeah.
Seems enjoyable.
So I have one important question, but I would probably give panelists only 1 minute to answer because I don't really want to take away. And before that, Neeraj, could you give me?
Yeah, sure. Great question, right? You get this.
So
deep learning for coders book for that? Or,
Nominate.
So the next question that we have for the panel is what breaks at scale? And we know everything breaks at scale. That's why scale is challenging and exciting both at the same time. And I want to start from this side. Peter, what's one anecdotal story or a viewpoint or anything that you want to share around what breaks at scale? And remember 1 minute.
Yeah, I'll keep it very brief. I think what breaks at scale, especially if you think of organizational scale in the enterprise, is just that there's lots and lots of data everywhere. And I think, data mesh gets talked a lot of at meetups like these, but, the discoverability, data catalog, and the like, these are really, really important because, oftentimes I've seen sort of like machine learning teams building similar stuff to basically the stuff that the business analysts and the data analysts are building. And, that sort of, discoverability of different data sets. Now that might be a little bit of a tangent to what the question was sort of getting at, but, because, potentially what we're thinking about what fails at scale is sort of like, okay, billions of requests per second or something like that. But I think there is like some sort of organizational scale that many companies get to, and they sort of have these breakdowns where I guess there's organizational inefficiencies going on, and because of a lack of structure, lack of what they call DATSys or whatever in the data mesh space, that doesn't allow for I guess an efficient organization that can really be leveraging each other's work, a little bit like an ecosystem of microservices where there's like an app mesh or something like that. That's kind of how I almost envision data mesh in practice in a large organization, that ability to sort of tap into those various data sets, leverage each other's work.
Thank you.
I think to answer your question, what breaks at scale? I think not everything breaks at scale. Things that we have already thought about scaling, they tend to not break. I've seen systems where we knew beforehand that, yeah, we are going to get, Black Friday spike in an e-commerce platform, and we built the system for 10 million messages a second, and it was able to handle 1 billion. But those are the kind of systems that are easy to build for scale. I think the surprising piece of things breaking at scale is where we do not anticipate there to be scale when we are designing our systems. A good example, a lot of times I've seen when people design their data storage, it's a pretty much solved problem. If anyone is using AWS S3 for their data, it's infinite scale for you at that, and you can hold petabytes of data. But what I've seen break at scale is the lineage that goes with it because of the graph nature of the metadata about your data. And as we progress further into the use cases that we are refining over time, you would start to notice that as your data grows linearly, your lineage grows exponentially. And that's the kind of thing that you want to build with 10x, 100x, 1000x scale in mind. You might not need it today, but your tomorrow self will thank you for it.
Yeah, that's a very good point. So I guess we have to think about all kinds of problems when we are building simple things.
Well, you've got a minute, so I'm going to come up with 2 super quick examples of things that break at scale. I was working with a financial services company. You can imagine credit decisioning, customer steering, customer experience. We used to plan this for 1,000 simultaneous user sessions. We built it, we tested it, we load tested it. It was working brilliantly. And then they acquired another company and we had to go up 22-fold in customer traffic. In short, we only had a few weeks and we solved it with some good old data engineering stuff. We put aerospike there to hold, solve for some low latency stuff. And we also put some feature stores under the cover to help with looking things up. So sometimes if you know that you've got a massive growth on your horizon, you can solve it with scale engineering. I've got another fun story. We worked with a drone delivery company, as in drones that delivered food. And we were doing this with some really, really basic experiments. We had essentially one drone in the fleet, and we basically had to work out when it was landing, whether it was ready for another delivery. And this is had about 75 odd features, feature values from the drone. We had to quickly determine when it landed, whether it was good for another flight. Now this worked really, really well. We built a little model that actually gave it the thumbs up or the thumbs down before its next flight. And when this became a bit of a scale problem was when they turned it on for 150 drones. And we solved that using Kubernetes because basically it was just exactly the same problem. It was easily scalable and we just ran lots of models whenever the drone landed. We could actually work out whether each and every drone was ready for its next flight. Super interesting stuff. Drones are cool.
What I am hearing is Kubernetes is cool. Just solve
Kubernetes is cool. Drones are cool. Kubernetes and drones, super cool.
100%. It's cool. Nagita.
Yeah, maybe I would just say everything around the data engine can break unless these guys are building some super cool solutions and safeguarding everything. On that, Kubernetes is cool. It is cool until it's not. You should talk to the output system guys, and that's another example that if you run in huge scales, everything has a chance of breaking. They were battling with these issues that every cell from a pod will go missing without recording properly, and they were causing gap in the output data. So there is never enough tests to build. You need tests everywhere. Also, as part of the full data engine, often dealing with humans. And humans are weird. They do strange things. So a lot of things which might make sensible at the design stage. If you're working with diverse sets of labelers or a diverse sets of team, maybe they're from a different language background, maybe they just take a different aspect on the instruction you're giving. And the whole thing needs to be future-proof and have tests everywhere. All I can say is there's never enough tests. Build more. You think you do anytime we're thinking you're doing it too much, still it's not sufficient.
That is a true story, actually.
Yeah, questions. We've got questions. Right.
When I heard all of that, only thing which came to my mind was Elon Musk breaking the glass in the demo. That's the biggest break I've ever seen.
Data labeling requires lots of time and effort, and you said that if you outsource this task, it always can be problem with instructions and how labelers understand these instructions. But did you try to implement any semi-supervised learning, like a method pseudo labeling for your data to automate labeling?
The best person.
Automated labeling, Harry, yeah?
Or
I think probably start with
that was
Nagita.
negative.
Okay, cool. Sorry, my bad.
It's a very semi-supervised thing.
Yeah, definitely. That's definitely good. And the multiple point in the system that you can use semi-supervised labeling, and we're doing it. This is something which I'm sure you've heard of it in the industry. People talk about moving from software 1.0 to software 2.0, moving from this heuristic-based system to data-driven system. We just did like a quick spark work using a previous rule-based system to generate data for like a land-based system. And usually when you're doing something like this, especially when like your different models or different systems have different inductive bias, even when one system is making a mistake, the other system, which is using the output of the first system as auto-label, can recover from some of those noise because it has a different kind of inductive bias. So definitely auto-labeling is great, but at some point, and that's definitely really efficient to bootstrap and get you to that like 90% accuracy quickly. But to move beyond that 90% accuracy is where you need to find these weird corner cases that your method is still not catching and the auto label is not sufficient, and then use human labelers for that. So it's not one or the other, it's a combination of both.
Can I ask something related? What's it about synthetic?
Sorry, can we hold on to that? Please hold on to that question a little bit. Let's see if anybody else wants to add anything.
Sorry.
Oh,
Any of you want to add anything to that?
I wanted to hear the question actually.
Sorry.
So what's your sort on synthetic data? Like, what is now? Like you say, like it's hard to get the edge cases. You could just generate them if you wanted to. Have you tried that?
I'm going to lose some cake today.
Synthetic is good once you know what you want. If I'm not aware of a dark pool cover with a grid on it at all in my life, then I can't build that in the synthetic data. But if I want to have a large data set of, say, construction crane, but I don't have access to lots of data, then that's where the synthetic data can be very useful, because I can then generate lots of examples from a few sets of examples. But again, it's a combination of both. It's not one or the other. Synthetic data is good in some narrow cases where you don't have access to do the huge data mining. If you don't have access to 1 million square kilometers of images to look for something, then synthetic generation is a very useful technique to start. But generally, there are some weird things in the world that you need to upfront think about those things if you're going on the synthetic data journey.
I was just going to try and ambitiously answer two questions at the same time. Go for it. Do I get a book if I manage this?
You get the coffee cup.
Okay. We're actually working with essentially an online company at the moment. And one of the challenges that they have is essentially content moderation of images. It turns out when you allow the random internet to upload images, you end up with some interesting legal challenges and some compliance challenges, and also some workforce management challenges. So when you're talking about actually being able to guard against some really, really unsanitary images, some really, really graphic images, and you actually want to think about both how do you prevent that from a legal perspective, how do you protect your end users, and how do you protect your workforce who actually have to label some of these images. There's actually a good combination of being able to tag and image some unpleasant data and have some reinforcement learning and some semi-supervised learning that actually can help moderate things in the real world. I mean, it's also a really interesting jurisdiction problem. We actually end up having to have some child exploitation material held in some geographic regions to train our models. we're not allowed to have humans look at that, and we're not allowed to host that in some regions. We have to train our models. So we end up with both jurisdiction problems, training problems, and human protection problems, and we can actually solve several of these simultaneously with reinforcement learning over images that we've already tagged, and we can actually have some semi-supervised learning to help reinforce and learn those models as we go. So some interesting sort of crossovers between those two questions.
I think I want to add one thing.
Yeah.
So I think if we go back to both the last two questions, the large part of it was how can we avoid labeling and produce more data? And while there are a lot of algorithmic approaches like synthetically generating, there's one aspect of it that rather goes underappreciated, like how can you more generate data from the knowledge that you have prior. So for example, ontology is a good example. You can use ontology to build more data, or you can use a prior data, like you can use government data for location where forestation is. You can use that data to augment and build. So I think there is an aspect of algorithmic engineering where we can use prior knowledge to reinforce and build that data. But obviously the aspect of weakly supervised learning and synthetic data generation is definitely at least.
Awesome.
One more question.
Yeah, I was just going to really quickly, can you provide a definition of synthetic data? Because up until recently, I didn't really know what it was either.
Do you want to?
Sorry,
So the question
That is
is,
correct.
what is the definition of synthetic data? I think in simple language, the synthetic data is you synthesize it rather than you actually getting it from the source or from the real sense. So you can use a model to generate, like GAN-based. You probably have heard about celebrity faces being auto-generated. That's a synthetic data because that's not a reflection of what is true image, or doesn't really represent a real object. You are synthesizing it.
I guess like an example would be like, say, if you
I'll
wanted
try
to.
an example. So we have already talked a bit about the use cases of cranes. So an example of non-synthetic data is you fly a plane and take images of a crane. Synthetic would be you code in Unity a 3D world which has cranes in it, and then you take a top-down picture of it, and it's synthetic because you just completely generated it.
Yeah.
Awesome. Does that kind of answer?
Yeah, that's one, and plus like you can think of blended when you take a picture of an actual crane, but then put it on different context on different background. So like a crane on the road, a crane on the construction site, a crane on a ship. Like if you don't have examples of this, but you have examples of a road, a construction site, and a ship, and multiple cranes that you can build is by blending different. That's another approach of synthetic data generation.
Well, that's something tonight.
Yeah.
Unity. Another use case for Unity.
Or an excuse.
We've got one more question there, so I'll quickly run over that side.
Can I just call out that that's probably the last question, given we have a call talk from.
There was a mention earlier about where things break at scale is when lineages become too much complex. In your experience, what principles or guidelines do you think work quite well to manage and simplify these lineages?
You volunteering to run with us? Go for it.
I think for lineages, I think the idea is instead of treating metadata, which is how lineages are usually treated, you treat them as actual data and you build for that scale. For example, because lineages are very graph-like, key value stores are very good at scaling with lineage kind of information. Obviously, the scale doesn't just stop at storage. Your scale also, the bottlenecks that you would deal with is how you process your graph. And that, again, would depend on the kind of use cases that you have. But graph processing on key value stores. It comes in handy quite a bit.
Just really quickly, I mean, I think, when you're talking about lineage and the like, thinking in a similar vein to sort of how you'd structure your data products in a similar vein to sort of like microservices, splitting them up into business domains and subdomains. And so having, not this one big monolith of a data source, if you will, or a data product, but just kind of having them well sort of labeled and structured and compartmentalized, a bit along the similar lines to sort of your applications, and and having that, I guess, typical sort of raw, unstructured, processed gold standard data, broken into those different domains. That's kind of, I think, where you're going to see wins at scale, if you will. No, Simon, nothing to add? Okay. Awesome. I'll hand it over to you, Sunita, to wrap things up.
Cool. I just wanted to thank everyone for all your attention and also all the interesting questions. They were really, really good. And also, thanks a lot for panelists for being patient and answering my questions. It was nothing personal. And I'll pass it on to you, Peter.
Awesome. We're going to round of applause for everyone, especially our awesome MC tonight, Anita. So up next, we're going to end the live stream now. We'll have just a quick drink break or toilet break, grab a slice of pizza, and then we'll get the Canva team up for their really awesome Secret Squirrel talk. It's probably not so Secret Squirrel. It's just in a couple of weeks' time they're going to be presenting it in Vegas, and we don't want to sort of ruin the big surprise. So anyway, thanks so much for turning out in such great numbers and listening to our awesome panel. Thank you.